Hey there. Ever wondered how something as notoriously absorbent as a black hole, something famous for devouring light, can also produce some of the most powerful jets of energy ever observed? I mean, think about it. Jets that outshine entire galaxies and span thousands of light years. Seems like a paradox, right? Well, today, we're diving straight into the heart of this mystery. The Blandford-Znajek mechanism. Buckle up, because this is going to get wonderfully complex. Alright, so for context, we're talking about supermassive black holes, the giants at the centers of galaxies. These monsters weigh millions, sometimes billions, of times more than our sun. But they don't just sit there quietly. When surrounded by a dense disk of gas and dust, what astrophysicists call an accretion disk, some black holes become incredibly active. They not only consume matter, but also seem to spit some of it out in narrow, extremely powerful jets. The question is, how does that work? Here's the pop-sci version first. The Blandford-Znajek mechanism is an astrophysical process that steals rotational energy from a spinning black hole and channels it into those relativistic jets. Now, remember that term, relativistic jets, because we're talking about particles being ejected at speeds close to the speed of light. It sounds almost magical, but it's actually all about magnetic fields and rotational dynamics. Now let's get past the pop-sci glaze and add more details. Okay, so imagine this. A black hole isn't just a singular object. It's surrounded by a magnetic field, shaped by the hot plasma in its accretion disk. If the black hole is spinning, and yes, most of them do, it drags the very fabric of space-time around it. This is called frame dragging, a prediction of Einstein's general relativity. Stay with me here. The dragging twists up the magnetic field lines around the hole like a giant cosmic whirlpool. These twisted magnetic fields can serve as a kind of bridge, a link connecting the black hole's rotational energy to its surroundings. Physics at its most dramatic, isn't it? Now here's where it gets juicier. The Blandford-Znajek process, named after Roger Blandford and Roman Znajek, who described it in 1977, specifically focuses on how these magnetic fields extract rotational energy. Picture it like this. The magnetic field lines are so tightly wound and intense near the spinning black hole that they become anchored into the event horizon, the outer boundary of no return. Because the event horizon is rotating with the black hole, it's effectively charged with energy. The magnetic field then acts like a dynamo, converting the black hole's spin energy into electromagnetic energy, which powers those insanely bright jets extending far into outer space. But of course, this isn't just a one-size-fits-all mechanism. There's some real debate among astrophysicists about how exactly it all comes together. For instance, one big question is the role of the accretion disk itself. Does the disk primarily act as a supportive environment for maintaining the magnetic field, or does it actively feed energy into the jets too? And what about the material being shot out? While Blandford-Znajek emphasizes electromagnetic energy, some evidence suggests that matter from the disk may still hitch a ride and feed the jets. Theoretical arguments aside, let's touch on the numbers to appreciate the scale here. The rotational energy of a supermassive black hole can be immense, something on the order of 10 to the power of 50 erg-seconds. Yeah, that's 50 zeros after the 10. Compared to this, even the entire output of the sun is peanuts over its entire lifetime. And now, for the most advanced part of this discussion, the unresolved controversies. At the heart of the Blandford-Znajek process is what we call magnetohydrodynamics, or MHD for short, the study of plasma interactions with magnetic and electric fields. Many simulations show the Blandford-Znajek mechanism works beautifully in computer models. But experimentally? Well, it's a bit like peeking through a fogged-up window. We don't yet have the observational resolution to observe the intricate workings of magnetic fields around black holes in real time, though tools like the Event Horizon Telescope are just beginning to lift that curtain. Beyond that, there are competing theories challenging Blandford-Znajek. Some suggest that disk winds, rather than rotational frame dragging, could play a dominant role. Others argue that the entire premise could be limited to specific conditions, like black holes spinning very close to the speed of light. Yet, despite these debates, the mechanism has stood its ground as one of the most robust explanations for astrophysical jets. So, why does this all matter? Beyond the sheer sci-fi thrill of understanding something so extreme, studying the Blandford-Znajek mechanism can help us decode how galaxies like our own Milky Way evolve. The jets don't just look cool, they have tangible, measurable effects on the gas and stars in their path. They heat up their surroundings, disrupt star formation, and redistribute material on galactic scales. And that's today's deep dive. If you stuck with me this far, bravo, you've officially gone beyond pop science. I love unpacking topics that challenge our understanding of the cosmos, and frankly, my ADHD brain revels in this swirl of complexity. Don't forget, we're a brand new channel, so your feedback shapes these episodes. And now, stay cruised, stay hyper-focused, and let's keep dragging space-time together.